So we're going to look at conservation of energy. And we're going to look at the most general form. And so this will be written as, we'll have kinetic energy at time t2 plus the potential energy at time t2 minus t1 minus v1. So that's our mechanical energy, or the change in that mechanical energy. This will be equal to the work done by all of the non-conservative forces. So F sub nc dotted with r dot dt. And you could further divide that up into dissipative forces as well as external forces. So this is our change in energy. And then this is obviously the work done by non-conservative forces. All right, if you are given initial conditions for a system, that allows us to determine what T1 and V1 are. And then if you're asked to compute the total energy of the system, we're really asking you to apply this conservation of energy equation here, where you will know what T1 is, you know what V1 is, then T2, V2 should be dependent on time, as should the work done by non-conservative forces. Okay, that's all we're going to say about energy here. Let me just see. We're going to now move on to impulse and momentum. And then we'll also deal with impacts as well in this section. All right, so we looked at linear momentum and also angular momentum. For every system, the linear momentum was simply the vector L equal to the mass times the velocity vector. And then just as a side note, that Newton's second law, it can be expressed as the sum of the forces is equal to the time rate change of the linear momentum. We also looked at angular momentum. For a rigid body or a particle going in the plane, we always used h for this, but for planar motion, it was simply I, about center of mass, times omega. Or if you were doing in some other point, then you would use parallel axis theorem to relate that. For 3D, it's more complicated, and we're going to skip that here. Instead, we're going to move on and take a look at the principle of impulse momentum. All right, so looking at for particles first, can write that the sum of all of the impulses, which are the integrals from t1 to t2 of f dt, is equal to the mass times the velocity at time t2 minus the mass times the velocity at time t1, or the sum of all of the impulses acting on the system is equal to the change in the linear momentum. Now, in this class, we really only applied this when we had some short duration force, but this equation is true even if you have a long duration or a continuously varying force. But it's most useful in cases where you have a very short duration like impulse or short duration force. You can also write this as the sum of the impulses, which we just wrote as imp from 1 to 2 is equal to the mass times the change in the velocity. We'll say r dot sub 2 minus r dot sub 1. So mass is constant, and everything we did here, mass was always constant. When we dealt with rigid bodies, we ended up with having to deal with linear momentum in two directions for planar motion. If you're doing 3D, you've got linear momentum in three directions. And then for planar motion, we also had a single angular momentum term. All right, so for our linear momentum, we're going to have that the sum of the impulses in our x direction from 1 to 2, this will be equal to the change in the linear momentum. So we'll have a speed v2x minus v1x. And then we'll also have the sum of the impulse in the y direction from 1 to 2. It's equal to the mass times the velocity or the speed v2y minus v2 or v1y. That's our linear momentum. We'll say linear impulse momentum. Or translational. We also then need to deal with the sum of the moments. And we'll just do center of mass here. Or we can do other point as well. About, let's say the center of mass first. This is going to be the sum of the integral from t1 to t2 of r sub I crossed with f sub I. Tau. So these are the moments produced by forces acting on body, any internal, external forces, plus the sum of the moments, and the sum of the integrals from t1 to t2 of the moment, say m sub I dt. And this integral should be with respect to t. All right, so then this is going to be equal to IC times the angular velocity at time 2 minus the angular velocity at time 1, which you can reduce down to scalars as well, since everything in this case should be in the k direction. We do sum of moments about any other point. We're going to get sum of the integral from t1 to t2 of Ri crossed with f sub I, or in this case, this vector Ri is the position from the point that you're summing moments to the force itself, dt, plus sum of the integral from t1 to t2, the moments m sub I dt. That doesn't change. In the first term, I mean, the expression didn't change, but the vector, position vector r sub I does change, because now you're looking for a different point. And then the angular momentum does change. So we're going to have I sub c times omega 2 minus omega 1 plus m times the quantity Rp crossed with V2 minus Rp crossed with V1. Where in this case, Rp is the the position vector from the center of mass to the point that we're summing at. The reverse of that is from the point we're summing at to the center of mass, and then V1 and V2 are the velocity of the center of mass before and after the impulse. All right, with that, we are going to move on over to impacts, which will be the last thing that we covered today. All right. So an impact is a very short duration collision between two objects. I'll just say impacts are very short duration collisions between two objects. Even if there are more than two objects involved, you will typically not have, I mean, it's not impossible for three objects to collide at exactly the same time, but it's very improbable. It's much more likely that two objects will collide just before they collide with another object, but not impossible. All right, there were two types of impacts that we looked at. Those are central and oblique. No, sorry, central and eccentric. And we can say that central impacts occur when the center of mass of each object lies on the line of impact. So it's when the center of mass of each object lies on the line of impact. And then eccentric impact occurs simply when the centers of mass do not lie on the line of impact. So eccentric impacts occur when the centers of mass. The centers of mass do not lie on the line of impact. So we only dealt with central impacts in this class, generally because we only dealt with particles. When we deal with rigid body impacts, which we didn't cover, so it won't be on the final, but in rigid bodies you tend to get more eccentric impacts than central. Right. There are two types of central impact. There's what we call direct and oblique. And we'll illustrate what each of these are with diagrams. So we'll put direct here, and then we'll put oblique over here. All right, we're going to draw two particles. Oops. Two particles impacting each other. And draw a line of impact. Make that a dashed line. And then we're going to draw a line that is tangential to the contact, also be normal to the line of impact. We're going to make that a dashed line as well. I'm just going to duplicate this image. Okay. I have layers, I do not. All right, we're going to call this bottom particle A, this top particle B. The only difference between direct and oblique impacts has to do with the directions of the velocity, the direction that the two particles are moving. In direct impact, particle A, both particles are moving along the line of impact. So their velocity vectors are pointing along the line of impact. And then oblique, their velocity vectors are not pointing along that line of impact. In dealing with direct impacts, you can change your coordinate systems to one that is on the line of impact. And in that case, everything turns into a set of scalar equations because you're now dealing with rectilinear motion during that impact. When we have some oblique case, you then need to determine, convert your velocities into normal and tangential components, and then you can switch back and do the scalar motion. So really the only difference is you have to do a decomposition in oblique. You have to convert or transform the velocity vectors from whatever coordinate system they're in into one that's normal and tangential, with the normal lining up with the line of impact, tangential being normal to that. All right, we're going to cover coefficient of restitution, and we'll look at the three different cases that we covered, and then we'll be done at that point. All right, so our coefficient of restitution is E is equal to the velocity of B after the impact minus the velocity of A. We've been using V, so let's do that. VB minus VA afterwards divided by VA minus VB minus. Here the superscript plus represents after, the superscript minus represents before. So where the superscript minus and plus represent before and after the impact. All right, and so just note that this coefficient of restitution is somewhere between 0 and 1. Cannot be greater than 1. It cannot be less than 0. When E is equal to 1, we have elastic impacts, which we'll talk about in a moment. Energy is completely conserved in that case. When E is equal to 0, we have what we call plastic response. Energy is not conserved. The only way E can be greater than 1 is if there's some stored energy in the system that is then released as a result of that impact. So if there's a spring compressed and then the impact then causes that spring to release, that would be a case where you'd have an E greater than 1. Or you would have an apparent E greater than 1. We're going to look at our 3 different cases. For case 1, we have that E is equal to 0. This is our perfectly plastic. So if E is equal to 0, this will lead to, just looking at our equation above, we'll be able to find here that VB plus minus VA plus, that must be equal to 0, or in other words, after the impact, the two objects are going to stick together and move with the same speed. So after the collision, the two objects stick together. And then we can write from conservation of momentum, we can write that MA VA minus plus MB VB minus must be equal to the sum of the masses MA plus MB times VA plus, which will just leave that as just a V plus. And then note that energy is not conserved in this case. right, the second case is when E is equal to 1, and we call this the perfectly elastic case. So E equals 1. This is our perfectly elastic impact. Right, impact up here. So this is a perfectly elastic impact. All right, so E equals 1. If we substitute that into the equation above for E, we'll find then that VA, or sorry, actually VB plus minus VA plus should be equal to VA minus minus VB minus. That's our first equation. The second equation comes from the conservation of momentum. We get that MA VA minus plus M B VB minus must be equal to MA VA plus MB VB plus. And you just need to solve these two equations simultaneously. All right, so note that energy is conserved in this case. So note that energy is conserved in this case.
So if you wanted to reduce conservation of energy, it's probably just more complicated than the other things.
It depends on what's happening. So like on the second midterm, you had a problem where you had a ball that was dropped and hit the ground. So there's an impact when it hits the ground, and if you want to understand what's going on during that impact, you'd want to use some of these equations. If you want to, understand what happens afterwards and relate what happened before, like long before to long afterwards, where that's a relative term here, you can use energy there. It depends on where you're looking at. So impacts are really thinking about like what happens right before and then right after. To expand a little bit, this T minus is really equal to the time of impact minus some epsilon. T plus is equal to the time of the impact plus epsilon, where epsilon is some really small number. It's a really, really small number. And we're really thinking about this in like the limit as epsilon goes to 0. So that's where impacts are really the most useful. So in the case of like that ball dropping and bouncing, we know that the ball goes up to some height. We can use that as a way to apply energy. In the case of, let's just imagine two particles floating in space that bump into each other and then bounce off and go different ways. That's a case where you wouldn't know anything else about their motion. And so you wouldn't be able to apply conservation of energy there. I mean, energy would still, if it's a perfectly elastic impact, you would still be able to apply that there. So it depends. I'm going to drag this up. All right, let's take a look at the last case, case 3. This is where E is not 0, but is also not 1. So E is greater than 0, but less than 1. This is known as an inelastic impact. we're going to get here that V plus minus VA plus, it must be equal to E times V, in this case it's VA minus VB minus. That's our first equation. And MA times VA minus plus MB VB minus must be equal to MA VA plus MB VB plus. And here you do need to again solve these simultaneously. And then in this case, energy is not conserved. So we'll just note that energy is not conserved in this case.